Hello, I welcome you in this session of 2-in-1 series, that is concept and practice. The subject is fluid mechanics, and this lecture, it is part 2, that means the viscous flow over the external surface of part 2. Okay beta. So before proceeding this lecture, I will share some information regarding IMS features. Okay. So what is that? This is the logo of IMS, and in this one I am requesting you just use like, share and subscribe that one, okay, the channel subscribe. Now there is another slide, is that your informatics slide, and that is your Telegram group. So what is the advantage if you join this Telegram group of IMS? You have to get a time to time schedule for the YouTube lecture, and also the PDF of that lectures, important updates regarding seminar and webinar, and also there is a information of the update regarding the PSUs and other government notification, expert session on important topic, and also the daily quiz. That is a very important question in which we have to discuss in the daily quiz. Okay. Now, so what you have to do, you just join this Telegram group, that is free of cost. Okay, no problem. Now next one is those candidates who are willing to join the GATE live online program for 25-26, that are the main features. What is that? You have to get 800 plus hour of live classes with the live interaction with the teacher. Also the second is the theory books. You have to get the theory book, exercise book, and in this exercise book there are 4,000 plus question, and there is a level 1, level 2, level 3 question. Okay. And 34 plus year of GATE question bank, and in this question bank you have a QR code for that one. The toughest question have a detailed solution also for the corresponding subject for the corresponding faculties. And also there is a 12 1-to-1 mentorship program is there, and also 130 plus online test with video solution of mock test. Okay. So if you want to get the more information, just call this number so that our counselor team will connect you and provide the proper information. Now that is the information. Now coming with the main topic, that is the boundary layer theory. So what we have to discuss already in the first lecture, what is that? See, we have to discuss the Navier-Stokes equation, and in that lecture we already told that this Navier-Stokes equation, what is the main consequence of the Navier-Stokes equation? The main consequence of the Navier-Stokes equation is that it is valid for the viscous flow. That means this is nothing, this Navier-Stokes equation is nothing, it is a conservation of momentum equation of the fluid that have a viscosity. So in the boundary layer flow over flat plate, we are discussing the external surface, that means flow over flat plate, and there are two-dimensional. So if this is a two-dimensional, my dear, if this is two-dimensional, just take this one, two-dimensional. Okay, the flow is two-dimensional, the flow is two-dimensional, then we have to disregard with the, so this is your, what is the consequence? When you have to analyze the boundary layer equation, the flow is steady. The flow is steady. So all the unsteady term is vanishes. The flow is steady, so this is 0. Why? Because this is 0. Why? Because the flow is steady, and the flow is two-dimensional. So we are not bothering about this Navier equation, which is in, this is your momentum equation in z direction. This is in z direction. This is your y direction, and this is your x direction. So in the z direction we don't bother about this equation. Okay. This first right side term is your net force, that means the force, that means this is your force per unit volume term. Okay. Now this is your x direction equation. In x direction equation we have to consider two-dimensional flow, so W component velocity is 0. Okay. We are not considering the gravity force, so this is 0. And also there are two-dimensional, so this is also 0. Now y momentum equation, two-dimensional, this omega is 0. third component. We are not considering the body force, this is 0. And also there is a two-dimensional, this is 0. Now my dear, and this equation not considered, okay. The fluid is incompressible and steady, that term is 0. So if you take the density, that means dou u over dou x plus dou v over dou y is equal to 0, and two-dimensional, this is 0. So these are the continuity equation in two-dimensional of steady incompressible flow, and these are the momentum equation in x and y direction. So we'll write this equation first, okay, these two separate equation, okay. We'll take the density divided by this term. So mu by rho, what is the mu by rho? Mu by rho, it is the also fluid property known as kinematic viscosity. So if you take this density divided, by here, and here we have also divided by this one. So what is the equation? U dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p by dou x plus nu d square u by dx square plus d square u by dy x square. This is x direction momentum equation. What is the momentum equation in the y direction? U dou u by dou v by dou x plus v dou v by dou y is equal to 1 by rho, here you have to take also in this one 1 by rho here, and here 1 by rho. So 1 by rho dou p by dou y plus, this is a kinematic viscosity nu, dou square v plus divided by dou x square plus dou square v divided by dou y square. These are the y momentum equation, and we are not bothering about the z momentum equation, only two-dimensional flow, and this is the continuous. So there are three equations is there. We'll write this equation. My dear. So x momentum equation, and mind it, these all are applied within the boundary layer. See, in this within the boundary layer. So within the boundary layer there is a viscous zone. We are not applying the Bernoulli equation in this zone. Bernoulli equation will apply above the boundary layer. Why? Because this is inviscid. There is no any shear stress is there. Okay, we will already discuss in the first lecture. So if you have any confusion, please go through the first lecture. Okay. So we are applying that Navier-Stokes equation and the continuity equation within the boundary layer. So within the boundary layer, okay, that means within the boundary layer, in boundary layer, we have to discuss in boundary layer. What is the x momentum equation? X momentum equation. What is the x momentum equation, my dear? Please tell me. Dou u by dou x, momentum equation, acceleration first. U dou u by dou x plus v, velocity in y direction, dou u by dou y, this is the acceleration, is equal to minus 1 by rho dou p by dou x, x direction, plus kinematic viscosity dou square u by dou x square, two-dimensional, dou square u by dou y square. This is the x direction momentum equation. Now, what is the y direction momentum equation? Momentum equation. What is the y momentum equation, my dear? So here u dou v by dou x, y plus v dou v by dou y is equal to minus 1 by rho dou p by dou y, now pressure gradient in y, plus nu, and the diffusion it is in y direction. Okay, so this is your y momentum equation, and the third one, this is the first, second, we have to require this three equation for the analysis of boundary layer, okay, flow over flat plate. What is that? Dou u This is your continuity equation. Continuity equation. What is that, beta? Dou u by dou x plus dou v by dou y is. These three equations you have to require. If you don't know these three equations, what is this equation? You don't know. If you know, see, that is the also in the YouTube lecture there is a series of the fluid mechanics. So if you subscribe the channel of IMS, so you have to get the YouTube free lecture. In that one we already discussed with the proof how we'll get this equation. Okay. Now my dear, so these are the momentum equation. Now what is the assumptions of this equation? The first assumptions is, what is the assumptions? Steady flow. Flow is steady and incompressible. Steady and incompressible. Second one is two-dimensional flow, 2D flow. Third one is no body force. No body force. Okay, these are the assumption of this equation. Steady and incompressible, and there is a not assumption, but the validity is your viscous flow. Viscous flow. Flow is viscous, real fluid. Flow of real fluid. Why viscous? If there is no any viscosity, the diffusion term is 0. But here the diffusion term is there. This is your kinematic viscosity. Kinematic viscosity. So if there is no any viscous, there is an inviscid flow, the diffusion term is 0. But here it is present, so we consider the flow is viscous. Now with the help of these three equations, we have to categorize the boundary layer theory. Start with this one. And now my dear, we have to, this is a very surprising, we are not any calculation part. Only we have to order of magnitude. With the help of concept of order of magnitude, we have to get the some more informative data, so that you can better understand the boundary layer. Okay, so there is no any numerical calculation type is there. Okay, only the order of magnitude. So what is the concept of order of magnitude? The order of magnitude, we have to take the order of any quantity of higher magnitude, and we have to order it, and we have to conclude it. That is the concept. Okay, so how? See this one. First one is continuity equation. What is that? Dou u by dou x plus dou v by dou y is equal to 0. This is a continuity equation. So what is the order of magnitude? That means we have to discuss with the scaling analysis, also called scaling analysis, or you can also say that order of magnitude analysis. Order of magnitude analysis. What is the notation of order of magnitude analysis? Notation is O bracket or. This one. These are the notation. These are the two notation of order of magnitude. Okay. So what is the order of magnitude of this first term? U. What is the maximum U? Is U infinite? Why? Because beta, we are discussing the model like that. This is your plate. Okay. This is a plate. This is your x is equal to 0. This is x is equal to L. There is a boundary layer, and we are discussing within the boundary layer. So maximum x is L. This is your y direction. This is your x direction. Above, the fluid is flowing with the velocity of u infinite, and here is the velocity of any local velocity u, and these are the varying. Now, so the maximum y is how much? Delta. This is your boundary layer thickness. The maximum y is delta. The maximum x, y max is equivalent to y max. Maximum value of y is equivalent to delta. Maximum value of x is equivalent to L. Maximum value of velocity component in x direction, velocity component in x direction, it is your u infinite. Maximum velocity in y component, let's suppose this is v infinite. These are the order type. We put the order type like that. So first term of the order of magnitude, the first term is the order of magnitude in maximum is u infinite, and x, the maximum x is how much? L. And this is your, okay. And what is the second term? What is this maximum? V infinite divided by what is y max is delta. Now my dear, summation of these two is 0. That means what is this value? The same in the negative form of this one, so that this value is 0. Understood or not? If this is your plus 10, so there is must be minus 10 is there. So order of magnitude are same. So these are the same order of magnitude. That means this order of magnitude is equal to this order of magnitude. Why? Because both are equal. Both are equal. What is the same magnitude is there? The same. Why? Because this summation must be 0. So what is the value of this one is the negative of this one, so that the resultant is 0. So these are the same. So from here you can easily find what is the value of maximum velocity in y direction. This is your velocity in y direction. So these are order of u infinite into delta by L. This is very important. Now my dear, take a look. See this one, this is important thing. Now very important conclusion is there. Ki sir, what is delta by L? L is the length of the plate and delta is the boundary layer thickness. And boundary layer, there is a first very subtle concept is that the boundary layer will be analyzed when there is delta by L is very, very small. That means length is very, very larger than the boundary layer thickness. Length is very high as compared to the boundary layer thickness. That means this consequence of this one, that means delta by L is less than 1. This is a very important, I am telling you. First consequence of this boundary layer. We'll prove it also, no problem. That means if delta by L, that means if delta by L, if, this is your if, and it is validation, कि sir, this boundary layer thickness is must be less than, very much less than, very less than as compared to the length of the plate. That means the plate length is higher than, more higher than the boundary layer thickness. So these are the first thing you have to must be think about that. Okay. So if you do that, what is that? So if this is less than 0, less than 1, that means this value. That means hence, what is the conclusion for that one? Hence we can write velocity in y direction, maximum velocity is very, very less than velocity, free stream velocity in x direction. This is very important conclusion is there. That means in this component velocity is higher as compared to the transverse direction velocity. Okay. Now, so if you analyze the boundary layer theory, someone asks you, what is the first assumption while you are analyzing the boundary layer theory? So you can say that, sir, flow over external flow for the external flow, example flow over flat plate the first assumption is very important, is delta boundary layer thickness divided by length of the plate is much less than 1. This is the first assumption. Someone asked you, what is the first assumption? That is, what is the main assumption? What is the basic assumptions while you are studying the boundary layer theory? So, while you are studying the boundary layer theory, the basic assumption is that, sir, the boundary layer thickness divided by the length of the plate is much less than 1. That means that very thin boundary layer thickness as compared to length of the plate. Clear? Now, now we have to discuss about the momentum term. So, these are the conclusion. What is the velocity? Why? Because we don't know. We have the x component, the maximum velocity we have u infinite, but y component maximum velocity we don't have. But see the beauty, with the help of order of magnitude, we conclude that the maximum velocity in y direction is equal to this one. That is the very beauty. This is the beauty of scale analysis. Yeah. Order of magnitude analysis. Now we'll use this equation into the momentum equation. So first we consider the y direction momentum equation. Okay. So what is the y direction momentum equation? This is the y direction. First we consider this one. What is the y direction momentum equation? This is the y direction momentum equation. Write down. Take y direction momentum equation. What is that? Y direction. U dou v by dou x plus v dou v by dou y is equal to kinematic viscosity y dou v square by dou x square plus dou v square by dou y square minus 1 by rho dou p over dou y. Okay, this is the y dou p over dou y. Okay, now we have to scaling it. Now we have to order of magnitude. We find the order of magnitude. So what is the order of magnitude of this one? Please tell me. What is the order of magnitude of this one? Order of magnitude of this one. U is the maximum, u infinite. V is the maximum, v infinite. Divided by x maximum is how much? X maximum is how much, beta? X maximum is how much? L. What is the order of magnitude of this one? V, v infinite. And this v, v infinite. That means v infinite square divided by delta. Yes or not? This v and this v, v infinite. Order of magnitude. Don't bother about difference. Order of magnitude, only you take the order of, don't bother about the numerical value. Don't bother about this differential term. Only take the order of magnitude. Okay, now. This order of magnitude is your what? So this is your right. Okay, now this is equal to, what is the order of magnitude of this kinematic viscosity property? So kinematic viscosity. What is the order of magnitude of this V? Okay, this is not like that. This square is here. Okay, now what is that? V infinite divided by, this is your L square, yes or not? Is the order of magnitude. This is your V infinite divided by del square. Okay, minus order of magnitude, don't put the minus. Order of magnitude 1 by rho P. Now you don't know. So what is the gradient of, what is the del P here? What is the order of magnitude of del P? That is a very important. We'll discuss this thing also. But now you have to take one look is that, see, this is your y, this is your x, this is your boundary layer. Okay. Now this is your delta. Let's suppose this is your delta. So, and this is your length L. This is your length L. Now, and here is the u infinite maximum. So, for the maximize this u infinite, and mind it, this is outside the boundary layer, and outside the boundary layer we'll use the Bernoulli equation. So, what is the Bernoulli equation? Pressure, change in pressure plus kinetic energy plus potential energy. Pressure energy plus kinetic energy plus potential energy is constant. That means the pressure energy, if you neglect the potential energy, that means the pressure energy, change in pressure energy is the order of magnitude of the kinetic energy. Change in pressure energy is the order of magnitude of the kinetic energy. And mind it, beta, why we are discussing, so these equations are valid in the boundary layer, but why we are discussing outside, we'll discuss. Ki, sir, this pressure gradient is within the boundary layer, but your analysis above the boundary layer, how? We'll discuss. This is very subtle concept, I am telling you. So, what is the order of magnitude of outside? Delta P, order of magnitude is kinetic energy. Kinetic energy is what? Half rho u infinite square. Half rho u infinite. So, neglect the half. So, this is your rho u infinite square. These are the order of magnitude outside the boundary layer. Okay. So, what is the pressure change of outside the boundary layer? We'll use for the inside also. Why? These are the very subtle concept we will discuss in the next series, third series. So, if you continue, then that is okay. So, here we will put, see, there is a confusion, lots of students confused, sir, here this equation is valid within the boundary layer, this equation is valid within the boundary layer, so why we are use the delta P above the boundary layer? That is the concept that we will discuss in the third lecture. Okay. So, what is that here? Rho. What is the delta P here? Rho u infinite square. And what is the order of magnitude y? This is delta. Clear? Now, see this one. Now, so these are the order of magnitude. Okay. So, this order of magnitude here. So, u infinite, what is V? Order of V, u infinite del by L, u infinite del by L square. Order of magnitude, what is V infinite? U infinite del by L. So, u infinite del by L, that means del 1 by delta u infinite del by L, yes or not? U infinite del by L square. Okay, what is this one? Order of magnitude, you can take equal, no problem. Kinematic viscosity, what is V infinite? U infinite del by L. So, there is a L square. U infinite L square, okay, no problem. So, L cube put here, no problem. Order of magnitude, what is this V? U infinite del by u infinite del u infinite del u infinite del by L, u infinite del by L del Q. Okay, what is this order of magnitude? Same, 1 by rho u infinite square by del. Yes or not? These are the order of magnitude, all this thing. Now, my dear, very important thing is there. Very important thing. See, my dear, we analyze that, we already analyzed that. If you solve this little bit things, okay, no problem. We'll discuss this thing. This portion, very important. This portion we'll discuss. So, if you take this one, my dear, so what is this one? kinematic viscosity V infinite by L square, yes or not? L square is there. The order of magnitude kinematic viscosity V infinite by del square. No, my dear. See, if we multiply here, what is that? Del by L. So del by, if you multiply delta square, if you multiply both sides delta square, so delta by L whole square mu V infinite is the order of magnitude. Here delta square. So this is a V infinite. Yes or no? Multiply with delta square. Both side we multiply delta square. No, my dear. See, very important. Very, very important. What is that? Delta by L is very minimum. That means this term is very, very minimum as compared to this term. That means this term is this diffusion. This is the diffusion in x direction, and this is diffusion in y direction. These are diffusion term. Diffusion in x direction. This is diffusion in y direction. So diffusion in x direction. This is the diffusion. This is the diffusion in x direction, and this is the diffusion in y direction. So diffusion in x direction. Why? Because this is delta by L, and delta by L just now we have less than 1. So this term is that means diffusion in x direction is very, very, very negligible as compared to diffusion in y direction. So you can neglect this term. Okay. So my dear, I will stop here and will continue in the third lecture. That is the very important thing, consequence of this one. Now the main part is opening. The main part is opening. So stay tuned and please wait for the third lecture. Up to that, thank you. Bye-bye.